thank you, the person who put the table, the chair, to keep the door unlocked. So, another example of a thin film interference. But before, good morning. So, that's a standard situation. What is a thin film interference situation? When we have a thin film between two large media. And every time we have to think about the same thing as, for example, we have to make a choice here at the top boundary when the first ray is being reflected. Does the wave flip? Is there a phase shift or not? The same question we should ask about the second boundary when the second reflection is happening. We also have to think about what equation to choose for effective path length difference, for the constructive interference, for the destructive interference. And of course, when a number represents a wavelength, we should think about where. So, what do you think? For the first reflected ray, what answer should we choose for that variable which represents the phase shift if it happens? If it doesn't happen, of course, that should be equal to 0. But if it does happen, it should be a specific number. And if we do it right, of course, we can repeat the same approach, the same reasoning for the second boundary. And that will give us the effective path length difference. We just have to set it to right condition and solve it mathematically. And here we just need to remember rules. When light travels from a medium with a higher index of refraction into a medium with a lower index of refraction, the mnemonic rule says it's like a heavy to thin rope situation. And in that case, there's no phase change, no phase shift, no additional half of a wavelength should be added. In the opposite situation, and what is the situation happening here? So let's talk about this one first. Delta T. This is like thin to thick, or we can just see the numbers and remember the rule. It says, it's first of all, it's not 0. Okay, if it's not 0, what is it? Well, it has to be a half of a wavelength. That's the wavelength. Where 469 nanometers, that's the wavelength where? Vacuum or air. But this wavelength should be in the film, and the index of refraction of the film is 1.4. How do we know? We can see it right there. So what should be right? 469 over 1.4, 1/2. and that will be nanometers. Right, so, and for this one, so this is air or vacuum. And here, delta B, that should be 0, because 1.4 is greater than 1.33. No shift. That's the most important part of it. Now, so again, just keep in mind, we have to make choices. Yeah. Life is always about making choices, right or wrong. This is not about making a choice that just have to be memorized. That's a part of a knowledge. That's a wavelength in the vacuum. Now, you also can just, well, it's your choice. You can know the rule when reflection happens with a shift or without, or you can just memorize 4 cases. That's only possible cases for the top phase shift, for the bottom phase shift. Nothing else can happen. So whatever faster, better for you. It's your strategy. Now we just have to apply that strategy. So the effective path length difference, or delta effective, or delta R effective, many symbols can be used, always equals 1 thickness because the ray travels down, plus second because it travels up. But now we also should add a half of a wavelength in the film. We just have it proved. Now, again, what we want to do is we want to eliminate a certain color. So this is the keyword. Yeah. That's sufficient already to figure out what condition should be used. Elimination means these two reflected waves should cancel each other, which means the effective path length difference should be equal to odd number of halves of a wavelength. How do you write an expression for an odd number? That's up to you. Yeah, well, we just need to remember that. Now, because that's supposed to be the same expression, this plus this should be equal to, I prefer using a different letter M to describe an odd number. And we have to solve it for this variable 2m minus 1, a half of a wavelength in the film, minus a half of a wavelength in the film divided by 2. And of course, different m's. In general, technically, this m could have any initial value, but only that makes sense, which makes this thickness, well, making sense. And in this situation, naturally, it has to be greater than 0. So this is how we can simplify it. 2m over 2, m times wavelength minus a wavelength a half of it and a half of it, and divide it by 2. M equals 0 gives a negative number, M equals 1 gives a 0. So the first non-zero thickness is reached when M equals 2. Which gives a half of a wavelength in the film, 469 over 2, and the index of refraction of the film. So we have solved on Friday a problem for constructive interference. Now we have solved the problem for destructive interference. That exhausts all our options. 469 divided by, well, 2.8. Once, well, round it up. The better I try to make it, the worse it looks. Okay, 2. Well, that's it. And this phenomenon, as again, is being used for making some specific color, like red, for example, disappear from reflection. And we just have to use the coating with the right value for the index of refraction and the thickness, and that's it. So, and we are done with thin film interference. Well, but we still keep talking about properties of light. And because it's physics, lots of situations in physics begin from observations. And this is one of those standard observations. You have some material, you place it, making light traveling through. You can see that light becomes slightly dimmer, which is natural. It's being partially absorbed, maybe even partially reflected, partially transmitted. That's nothing interesting, but if we take a second one and we place on the top of it, and we start rotating it, we can see that the brightness, well, the brightness is a feature of human perception. Physically, we talk about intensity, the amount of energy traveling toward the screen changes depending on the angle from the same to 0. How can we explain this? Well, if light is a wave, what do we know about waves? 2 types exist, longitudinal and transverse. And for a longitudinal wave, that shouldn't be a deal, it shouldn't make any difference. So these experiments kind of tell us that a light is a transverse wave. A simple plain electromagnetic wave looks like this. Well, to make it fly, I would have to, I don't want to do that. It's a combination of 2 fields, electric field and magnetic field, which travel away in space. When they reach a conductor, for example, a retina has ions in it, electric field starts acting on those charges in the conductor, and those charges move. So electric field might generate electric current, and depending on how it happens, light might travel through or not. Of course, the total description of this, everything related to light or any type of electromagnetic wave is based on Maxwell's equations, and he was a genius, so that's beyond our understanding. But what we need to know, first of all, a visible spectrum is a tiny portion of a total spectrum of electromagnetic waves. We can generate those waves. How? Well, this is how. We need an electron, or technically any type of a charge, and we have to start it wiggling. And when it starts moving, electromagnetic wave starts traveling away. And if that electromagnetic wave reaches another electron or another charge which can freely move, it makes it move. That's it. So we have a source, we have a test charge, and that's basically an idea which works for radio, TV, and any type of energy transmission, including light energy transmission. So the visible spectrum is confined between about, oops, oh, shoot. Can I fix it? No. Why? Yeah. Windows and Mac hate each other. It's been done on Mac, and now Windows punishes us for that. So that should be 14th. That's 10 to the 14th. Those are the frequencies which limit the visible spectrum. Well, of course, it doesn't limit the spectrum of waves, electromagnetic waves. Yeah. Infrared, ultraviolet, etc., exist. And again, when electromagnetic wave travels and encounters conductors, it starts acting on those electrons in conductors. And electrons start what? They start generating their own field. And what might happen? Well, if electromagnetic field is parallel to conductive, well, lines, grid, it generates a strong electric current, and that electric current generates strong electric field, which actually cancel out the original one. It's like shielding. We had an experiment with a radio in a cage, same phenomenon. But if electromagnetic wave travels and encounters a conductive grid in such a way so electric field is perpendicular, it doesn't affect electrons, so it gets through without any change. So these are two extreme situations. And of course, in between this case, this direction, which doesn't affect wave, has a name, the transmission axis. This device has a name, a polarizer, and we will soon say why. So when the electric field of a wave is parallel to transmission axis, it travels through without any change. But if electric field in electromagnetic wave is perpendicular to transmission axis, there is no transmission, light cannot pass through. So please tell me what's going to happen if light travels at a certain angle. So here I have a simple model. We don't need to see an actual device. Again, a device looks like this. It's not a conductive grid. Yeah, we don't see any aluminum rods, but it's a transparent material which has relatively long molecules which act like wires in a similar way. So this is a device which has a transmission axis in this direction. How do I know? there is a mark here. It says this direction. So we don't need the whole device. We only need the direction of a transmission axis. And a wave travels. So if a wave is perpendicular to transmission axis, no transmission. It cannot get through. It disappears. If a wave travels in such a way so electric field is parallel to it, it travels through. What's going to happen if there is a certain angle between the wave, well, we say it's polarized in this direction. This is a direction of polarization of a wave, which is direction of electric field in a wave. Well, we know that every vector has components. So we can break it down into two components. One component will be parallel to transmission axis and second perpendicular. What's happened to the perpendicular? It cannot get through. What happens to the parallel? It travels through. That's it. So in this situation, some light will travel through the polarizer. How much of it? Well, that's what we need to calculate. It's a geometrical problem. Here we have an original direction of electric field, a direction of polarization of this light. And this line, well, in my experiment, that would have been like this, like this, like this. This line represents transmission axis. So only that part of a wave which is parallel to it travels through. And if we know geometry, we know everything about this phenomenon. So, do we know geometry? Okay. We can close it. That's a question number 3. Geometry. 1, 2, 3, 5. Yes, we do know geometry. Of course, it's just a standard right and triangle. This arrow is what we could call the component which is perpendicular. This arrow is the component which is parallel to transmission axis. What does A and B mean? Well, B means before the polarizer. A means after. Again, a standard kind of notation. So before the polarizer, like electric field in a wave has a certain direction. What does a polarizer do? Two things. It changes the direction of the polarization of light. After the polarizer, light should travel only having this direction for polarization for electric field. Plus, it also changes the strength of the electric field according to the geometry. The hypotenuse, the angle, over hypotenuse should be equal to cosine. Cosine of what again? If we write a variable, we need to know the meaning of it exactly, and we have to be able to say it out loud. And the picture says that is the angle between the transmission axis and direction of polarization of light, which, as we know, is just direction of electric field. That's it. So that's what we need to know. The direction, the orientation of transmission axis and the orientation of polarization of light. But well, that's the answer. What we see is not electric field per se. We see the intensity of it, brightness. And intensity of a wave is proportional to amplitude of it squared. So we have to square electric field. And when we square electric field, we get the so-called Mauss's law. This is the intensity of light after the polarizer. This is the intensity of light before the polarizer. And this is the angle between the transmission axis of the polarizer and the initial direction of the polarization of light. That's it. Well, theoretically, technically, light is a wave, oscillates, but it happens so quickly. So our eye only registers the average value of that. So nothing is time dependent in this equation. Well, again, this equation only works when light was already polarized initially. How? Don't care how. We just need to know that it was already polarized. In that case, we can apply this equation to relate the intensity before and after the polarizer. What's happening when it's not polarized? The regular light is unpolarized, but unpolarized means it is composed of all possible waves with all possible directions, all of them. Up and down, left and right, all possible. What's going to happen to the light when it travels through? Well, they all now have to be aligned in the direction of the transmission axis, all of them. But also, perpendicular doesn't get through, parallel gets through without being affected, and all others getting cut. So all we have to do is just calculate the average between nothing and maximum. And for unpolarized light, the intensity before and after related by just a simple coefficient half. For unpolarized light, which means actually polarized in all possible directions, the intensity after the polarizer is equal to a half of the intensity before. So now we know everything. What does the polarizer do? Polarizes. That's what it does. What does it polarize? Light. What does it mean? Two things. After the polarizer, electric field, direction of polarization of light becomes parallel to the transmission axis, and intensity is being changed according to a law, cosine squared or a half. So that's it, whole theory. If light is unpolarized, intensity just gets cut in half, but after that, light becomes polarized. If light is polarized, the intensity is related by Malus's law. Well, let's do a problem. So here we are looking for the angle between two polarizers. This is my experiment, basically. I have two polarizers, and I have a source of the initially unpolarized light. So what is happening first? The intensity is cut in half, but also now the light is polarized. And this mark tells me the direction. So after traveling through this polarizer, electric field should point, well, parallel to this red mark. It is polarized. Now I'm placing a second polarizer, and this is a case when transmission axis of a second polarizer is perpendicular to transmission axis of the first. No light travels through. And I can find an angle which gives me intensity of, well, 10%, 20%, 40%, up to 100%. That's what we're looking for. So what is happening first? So the first transition. Well, we have to set the initial intensity to a certain value. And the new intensity after the first polarizer should be equal to just a half of this, because the light was initially unpolarized. What does a polarizer do? It polarizes. What does it mean? It also makes light be polarized. So this is the transmission axis of the first polarizer. So after this polarizer, light becomes polarized in this direction. And now it encounters the second polarizer. That's electric field. And this is the transmission axis of the second polarizer. And this is the angle we are looking for. The new intensity, the final intensity, which can be measured by a photocell, should be equal to the intensity before, which is this one, times cosine squared of the angle we are looking for. So we can combine these two expressions. Final intensity should be equal to initial divided by 2 and then multiplied by cosine squared. What else do we know? Well, we know that the final intensity should be equal to 10%, 1/10 of the initial intensity. So this is physics. This is an experiment. That's how we set that angle. We've been measuring the photocell until measuring intensity by a photocell until the intensity dropped to 10%. There's actually another way to describe this. Sometimes people say we need to find an angle that would change intensity by 90%, yeah? To 10% and by 90%. It drops by 90%. So final intensity should be equal to initial intensity minus 0.9 of initial, which of course gives the same. It's just a language thing. But we need to know it. So now we can combine these two equations together, right? 0.1 times the initial should be equal to 1/2 times the initial times cosine squared of the angle we are looking for. And see what happened? A miracle. That very variable we didn't know, it wasn't given to us. Doesn't matter because it is cancelled. Now we just have to solve an equation. Cosine of this angle should be equal to square root of 0.1 times 2. Square root. I don't need this actually. I know it's a number. What I need is this. The angle should be equal to inverse cosine of this 0.2. That's what actually we are looking for. Inverse cosine. Where is it? Here. Inverse cosine of square root of 0.2. I've got 63 degrees. $63.4. So the strategy for any problem related to Malus's law of polarization is always the same. Just look at the angle. Now, question to you. Again, the same experiment. I have two polarizers which are perpendicular to each other. So perpendicular means there will be no light traveling through the second polarizer at all, because after traveling through the first polarizer is already polarized, and now I aim it at the polarizer with the perpendicular. So there is See, there is some light, and now there is no light. Where is always light? At the end of the tunnel. But what I want to do is place a third polarizer. How? Not on the top. It's useless because there is no light already. I want to place it between those two polarizers. And of course, only two things might happen. Nothing or something. Nothing means there will be no light anyway. Or, yes, there will be some light traveling through now. So, if you think yes, there will be light, choose one. What I want to do, this is what I want to do. And of course, we can just see what's going to happen. I just need to slide it in. And we can see there is some light. What's happening? Well, of course, now the light which was polarized perpendicularly to the second polarizer, to transmission axis of the second polarizer, will be slightly turned by this middle polarizer, and now it's not perpendicular to this transmission axis anymore. And if it's not perpendicular, it does travel through. The problem with these type of problems is only one. It's hard to draw it. We cannot draw a wave, or, it might have many directions. So what I usually do, I'm imagining that I'm looking at the whole setup aside from the photocell. So what would I see first? So I would see at first unpolarized light and the first polarizer. And that would give me light polarized in the direction of the transmission axis of the first polarizer. What do I do now? What do I see now? Now I'm adding a middle polarizer with the transmission axis at a certain angle. What does it give me? It gives me light now polarized in the direction of the transmission axis of that polarizer. What do I do now? Now I'm adding the polarizer with transmission axis perpendicular to initial one, like this. Of course, I have to keep track of what is what. Yeah. So in this situation, this is electric field, and this is transmission axis number one. And now this is electric field, and this is transmission axis number two. And now this is electric field, and this is transmission axis number three. But I can see some angle, which is not 90 degrees. So light travels through, and actually it will be eventually polarized in the direction of the transmission axis of the last polarizer. And if I want to, of course, I can calculate the intensity before and after. We're going to do it. So that's the answer. We're going to do it right now for this specific problem. There is a standard agreement which we always follow. We measure angles normally from vertical direction, from y-axis. And if an angle well, for the polarization, by some reason, most people treat clockwise angles as positive, counterclockwise angles as negative. But because, again, cosine is squared, it doesn't really matter absolutely. We just have to treat those angles differently. So in this situation, we have to draw a picture which represents everything. First, linearly polarized the light. So it has been already polarized, which means there was additional polarizer used before. How does it travel? At turning to the vertical. Well, okay, I don't like it, but I have to follow this agreement. So I start from drawing a vertical axis. This is a positive number. So clockwise from that number, or from that axis by 20 degrees, that's going to be the electric field number 1. The initial intensity is 16 watt per meter squared. Well, that again, intensity describes how much energy travels through area per time through 1 meter squared every second. That's what it is. And the first polarizer has transmission axis at 50, again a positive number. So from the same axis, I have to go to the 50 degrees angle. That's transmission axis number 1. Now I can calculate the intensity number 1 for light traveling through the first polarizer. So all I have to do is be very, very careful with the angles. What number should I write for theta? Is it 20? Is it 50? No. According to a definition, theta has to be measured between the direction of polarization of light, which is direction of electric field, and transmission axis. That's theta 1. And our picture tells us it should be equal to the difference between 50 and 20, which is 30. All right, done with the first polarizer. Now, what do we have? Now we have a light with this intensity and the new polarization in the direction of transmission axis number 1. So this light now is polarized differently than before. But the second polarizer has its transmission axis at plus 20. Okay. Okay. So this is going to be transmission axis number 2. So now how do we calculate the new intensity? It should be the previous times cosine squared of theta 2. What is theta 2? Is it 20? Is it 50? No. Again, according to a definition, it has to be measured between transmission axis and electric field, which is, again, 50 minus 20. So I2 is equal to I1 times cosine squared of 30, which is 16 times cosine squared of 30 times cosine squared of 30. Cosine of 30 actually is square root of 3 over 2. If you know that, calculations can be done by hand, because if you square a square root, you get a simple number. And this calculation was done, and the answer is 9. That's it. So all we have to do is just draw a picture which tells us how to find the angle correctly. That's the only place where people normally would make a mistake. Well, so we saw the applet. To generate electromagnetic wave, including light, we have to use charges. We know a resting charge generates a static electric field, and that's it. When we have many, many charges traveling with constant speed, we call it electric current, that generates magnetic field. But if they start moving with some acceleration, slowing down, speeding up, that generates electromagnetic field. How? Well, the idea is simple. We know from the Faraday's law, changing magnetic field generates electric field. But Maxwell saw the symmetry in the nature, and he proposed that changing magnetic field should also generate electric field. So changing electric field generates magnetic field, changing magnetic field generates electric field, changing electric field generates magnetic field, changing magnetic field generates electric field, and we can continue on and on and on. And electromagnetic wave travels away. All we have to do is just take this capacitor and open it. And that's what we call an antenna. That's it. We just have to generate a relatively strong electric current, and electromagnetic wave begins traveling away from it. And of course, we use it for many, many different applications. Number one was the radio. Are you going to work today? Thank you. So a simple radio actually has a very, very simple structure. Well, we need the battery, a capacitor, and an electromagnet. That's it. Morse code. And if we have a receiver somewhere, that's it. How does it work? It's actually pretty ingenious. There's an electromagnet. It attracts a piece of metal. And when it attracts it, the circuit breaker breaks the circuit and it falls back. And when it falls back, it completes the circuit again, and it attracts it again, and it falls back. So it just makes many, many, many tiny sparks. We don't see those sparks, but they create electromagnetic wave traveling away, and that wave excites electric current in this antenna. That's it. Simple radio. Based on this idea, Rumford made so-called Rumford coil. You don't see the coil because it's a one built-in piece, but it has inside just much more strong conductor, electromagnet, and capacitor. What do I do? This is what do I do? This is what I do. It actually generates so high voltage, so it breaks the air, makes the spark. Morse code. And well, the next step was done by Tesla, because he invented Tesla coil. And Tesla coil, again, has just a very strong capacitor inside, and a coil. That's why we call it a coil. But move it away, because it can generate even stronger voltage. It can make even bigger sparks. Let's see. And Tesla actually was dreaming of using this for transmitting energy in space. Well, he was so obsessed, eventually he just got crazy. But the idea actually was correct. The energy can be transmitted. Power between the ends of this light is large enough, voltage is large enough to lighten up. Well, energy, of course, decreases when we move away. So drops very quickly. That's why Tesla couldn't actually make any use of this idea. Energy, unfortunately, is very hard to transmit without wires. Well, the last, what is it? Well, like actually, the last experiment demonstrates that the light is indeed, well, electromagnetic wave is indeed a transverse wave. This is a very old-fashioned so-called shortwave radio. It has an antenna here, and you see, this antenna generates electromagnetic wave, which generates electric current in the receiver, strong enough to light the bulb on. But what's going to happen? Well, first of all, if we move away, of course, see, energy drops very quickly. But what's going to happen if I turn it perpendicularly? That's it. This electromagnetic wave is polarized, and now it cannot excite electric current in antenna, which is perpendicular to this. Back again. So light is a wave, and that wave is not longitudinal. That wave is a transverse wave. Unfortunately, very soon we will have to challenge this statement. But before, let's go back to the slides. So, we are done with light. We're starting a new topic. We're starting the study of tiny, tiny particles everything is made of. This is our goal. You may think it's too much. Statistics shows it's not. Same question. We just have been convinced light is a wave, transverse wave, because all experiments prove that. The original particle theory, which worked good for reflection, refraction, was absorbed by the next theory, wave theory of light, because particles can't do that. Particles can't interfere, can't diffract. So naturally, light is a wave because light can interfere, can diffract. We know that. However, about 100 years ago, physics encountered experiments which could not be explained by the wave theory of light. Could not. For example, they could not calculate how much energy a simple candle should emit. They got infinitely large amount of energy any candle should provide. That's of course not the case. And Lebedev experiments show that light has a pressure. It's actually kind of was explained using wave theory of light, but it's much easier to explain imagining light, just particles bouncing off a mirror, like molecules acting on a wall and exerting a pressure. But the most important experiment was a photoelectric effect. It was discovered by Hertz, and it took almost 20 years to explain. The effect is actually very simple. You take a piece of conductor, you shine light on it, and you observe electrons being ejected by that light of a conductor. That's it. So The wave model provides certain specific predictions. For example, we know that electromagnetic wave has electric field in it. That electric field starts acting on electrons, so a force makes those electrons move. But what it means, if we crank up the brightness, brightness means we increase electric field strength, same color, same frequency, same wavelength, just brighter. Electrons, of course, should get more energy, stronger force acting on them, and they should be more energetic, but that's not happening. Just it. Instead, if we use a brighter light, we just get more electrons with the same energy. Bless you. So the solution was proposed by Einstein. He got the Nobel Prize for that. And he used an idea first, which came from Max Planck, that energy actually might be distributed in small portions. He just said, well, Planck thought that that was just a mathematical way to describe the spectrum. But Einstein says, no, it's more than mathematics. Light is composed of particles, photons. And those particles, like any particle, when they collide, there's a collision. The collision obeys, well, law of conservation of linear momentum, law of conservation of energy, and this simple mechanical model explained the phenomenon. Well, but the price was very heavy. Turns out we can't treat light neither as a particles or waves. It's some kind of a combination, which is much more complicated than we thought. And to describe light, we could use all variables which we used for particles and for waves. We just need to find a way to relate them. So photons, a tiny particle which never stops, travels always with the speed of light, but also can be described by a certain wavelength or frequency. And Einstein introduced, well, he used the Max Planck's equation, but he also added his own equation. And well, that has led to many, many relationships between variables which describe properties of particles and variables which describe properties of a wave. For example, a linear momentum, P, should be mass times velocity. Well, if we use that, and we know light travels at the speed of light, technically light should have a mass. Well, but it never stops, so it's a very strange mass. But also it should have a wavelength, because it's a kind of wave. And well, how would we relate wavelength and other variables? That relationship comes from Max Planck's equation. This is the energy of a single light particle, a photon, and this is the frequency of a light wave. See, even when we say it, it sounds strange. The energy of a light particle is equal to a certain constant, just a fixed number, times the frequency of light wave. Well, but that's what it is. This is a Max Planck's constant. He just introduced it to make sure that the spectrum he was calculated fit the experiment. Turns out it's a very small number. But if we know how to calculate frequency, and we know that frequency, speed, and wavelength related, we can calculate wavelengths. So there are many, many relationships which could be written for light particles or light waves. Let's do an example of this calculation. Wavelength, lambda, 620 nanometers. So we are looking for the energy. Well, the energy of a single photon should be equal to about 6.6 times 10 to the negative 34 if we use International System of Units. This is the value for max Planck constant times frequency. But the frequency, 6.6 times 10 to the negative 34, that's a 4, not a 9, I don't know. By now you probably should be used to already that you have no idea what I'm writing, but that's just a part of the experience. So frequency is equal to speed of light divided by the wavelength. That's it. We just have to take a calculator and calculate what it's going to be. Oops. Please also take a calculator and calculate 6.6 negative 34 times 3 times 10 to the 8th divided by 620 nanometers. So my answer is about 3.2 times 10 to the negative 19th. What unit should I write for energy? Of course, that's joules. We use an international system of units, meters, for the frequency hertz, and it hertz. And the Planck's constant is given in an international system of units, meters squared, kilogram per second. So that's the answer. 10 to the negative 19th. Have we seen this power before? Does it ring a bell? 10 to the negative 19th. What bell does it ring? May I make a suggestion? If you want to ensure that your life will be better, speak out. Thank you. Exactly. That is why for the quantum mechanical world, people have invented a new unit of energy. By definition, the amount of energy which an electron acquires by traveling potential difference 1 volt has a name 1 electron volt. So this is a name, electron volt, but it means energy. And of course, using this definition, the coefficient, the conversion factor is 1.6 times 10 to the negative 19. So 1.6 times 10 to the negative 19 joules, that's what we call 1 electron volt. Energy. Not potential, not voltage. Sounds like that, but it is energy. And of course, now, well, we can practice first in using electron volts, and then we can convert joules into electron volts. Question: a single electron starts from rest, travels through potential difference of 3 kilovolts. What will be its final energy measured in electron volts? The Tesla coil draws so much current sometimes it blows the switches. It happened before in this room many times. After Tesla coil was plugged in, energy was gone. So that's why I had to plug it in a different room, so it wouldn't affect my setup. So, if traveling through 1 volt brings 1 electron volt energy, how much energy does it bring if electron travels through 2 volt potential? 2 electron volts. 10 volts lead to 10 electron volts of gain. 3,000, that's what kilo means. 3,000 volts So initial potential is 0, final potential is 3000 volts. We, of course, could calculate work. Well, let's say magnitude, just we know it's going to be positive. It's accelerating. Could have been 1.6 times 10 to the negative 19 times 3000. That would be joules. But then, to get back to electron volts, we would have to do 1.6 times 10 to the negative 19 times 3000 joules divided by 1.6 times 10 to the negative 19. So, of course, it's going to be 3000 electron volts. So 3 kilo electron volts. 3 kilo electron volts. That's why it's a convenient unit. If we know the voltage, electron travels through that voltage, tells us the energy it gains in electron volts. So now we can finish this calculation. What will be the amount of energy of this photon, not in joules, but in electron volts? What would we have to do is calculate this joules divided by conversion factor, which is 1.6 times 10 to the negative 19, to electron volts. And of course, 2 is a much simpler number to comprehend than 10 to the negative 19. That's why we used electron volts. Now, we can use this approach for any wavelength. It doesn't have to be 620 nanometers. It would be any number of nanometers. Any number of nanometers. In the result, we get an expression which tells us immediately the amount of photon energy in electron volts. We just have to use that number in nanometers. It's not exact coefficient. For us, it's fine. For Weber sign, maybe the more accurate number should be used. So in our example, we would have to just replace this number with 620. So if wavelength equals 620 nanometers, the energy of a photon of that wave will be equal to this number of electron volts. It saves time. We don't have to use it, but of course we always can use the international system of units, but it takes more time. That's it. Well, now, backward problem. If we know energy and we need to calculate frequency or wavelength, what do? Well, we can, again, use international system of units. This is an example. This example actually gives us a coefficient, the max Planck constant, not in joules, but in electron volts. So in this particular example, the frequency will be equal to 2 electron volts times this coefficient. Well, different people use it slightly. Differently, power is different. 14 or negative 14. So I use usually 15. 0.48 10 to the 15. And 480 times 10 to the 12, that's terahertz. So If we know the frequency now, we can calculate the wavelength, but also now we can calculate the wavelength directly. Yeah. Well, approach number one, because speed, wavelength, and frequency related, the wavelength is equal to speed of the light over the frequency, 0.48 times 10 to the 15. And that will give us meters, but we have a different approach because energy and wavelength in nanometers related. We can calculate the wavelength in nanometers immediately. We just have to reverse this expression. And in this example, 1240 over 2, 620 nanometers, of course. So those are shortcuts, but I strongly recommend to practice with using those shortcuts. Different types of shortcuts can be used one way or another. This 1240 coefficient relates the energy of a photon measured in electron volts and the wavelength of light measured in nanometers, which is normally a case. Now, the photoelectric effect. I've learned about it when I was in the 10th grade because the mathematics is very, very simple. But at the time, the idea was ingenious, of course. If you have a photon which collides with an electron, the application of law of conservation of linear momentum leads to a Compton effect. That's a different story outside of the scope. But the application of law of conservation of energy immediately tells the Nobel Prize, but hundreds of years ago. So a photon has energy, which is equal to, well, in general, this. What might happen? Well, we have to look inside of a conductor. So there are electrons, atoms, well, lots of stuff. We are interested in a single electron. If a photon collides with it, that electron, after the collision, begins traveling. The base case scenario, it travels to the surface by the shortest path, and if still energy is enough, gets outside, and if still energy is enough, might travel away having certain speed. That's it. Of course, not every electron travels by the shortest path, so they might wander, so it might require more energy to bring him outside, but at least some of them might travel by the shortest path. So this energy of a photon might split between what? Between energy required to bring an electron outside, plus, if anything left over, kinetic energy of an electron. Well, technically maximum possible for this experiment. Some electrons might have a lower kinetic energy, so people use this, but normally they just write this, or mv squared over 2, and then assume that's a maximum possible kinetic energy of those so-called photoelectrons. A photoelectron is the one which doesn't remain inside, which is brought outside. And of course, the law of conservation of energy says that if we add the amount of energy used to bring electron outside, plus kinetic energy, we should get the original amount of energy provided by a photon. That's the law of the photoelectric effect. This term, well, first of all, people use different letters for that. It's called the binding energy, because energy are bound inside, or work function of that material, because some work has to be done to bring an electron outside. Of course, it's been measured for all major materials. So this is a fixed number. It depends on the material. For a copper, one number. For gold, another number. For zinc, a third number, etc., etc. So the law of the Einstein's law for the photoelectric effect can be written like this. Well, actually, just as we know, kinetic energy cannot be negative, well, in general. Hence, this difference cannot be negative, which means this experiment works, shows electrons ejected only if the frequency of light is greater or equal to this ratio. Only. It doesn't happen when the frequency is less. So this frequency has a name, the critical. So in order for the photo effect to happen, the frequency of light is supposed to be above that value or equal to. Hence, photoelectrons exist if the frequency of light is less than the critical one. No electrons are ejected. That's it. Now, of course, we can try different frequencies, measure kinetic energy of those electrons. It should be equal to this. In mathematics, this is a linear function. M represents the slope, B represents the y-intercept. So the graph should look like this, straight line. The slope tells us how to calculate the max Planck's constant. That's why this was so exciting at the time. But if we continue this line to look at the y-intercept, that gives us the work function, the binding energy of that material which is used in this experiment. This is a nice website, nice website with many interesting applets. This is the applet for photoelectric effect. You can choose different wavelength of light. Like right now it says yellow, yeah, and it shines on cesium, and let's replace it with sodium. Did you see what happened? Let's one more time. Cesium, sodium, cesium, sodium. There's one thing which changes, or two things: color inside that red bulb, which is a photocell basically, and this meter measures electric current. What is electric current? Number of electrons basically traveling per second. So when we use cesium with the yellow light, photoelectric effect does happen. Light ejects electrons. They wander in space. Eventually, they travel to a different electrode and travel through the multimeter. We can read the current. But if we replace the cesium with sodium, that's it. We don't see anything. Why? Well, because sodium has a larger work function, and the energy of the photons is not enough anymore to eject electrons. Now, what can we do? Well, we can try to change the frequency. Okay, it worked. If we replace yellow with violet, frequency goes up, more energy in each photon. So now energy is enough to eject electrons. What can we do now? Well, I'm applying electric field to these electrodes to bring electrons back. If I'm applying electric field, stronger, so now electrons will have to do more work to travel, and eventually, if I apply strong enough electric field by generating strong enough voltage, even the most energetic electrons cannot reach that electron, brought back, there is no electric current. So this electric potential of voltage, potential relative to zero voltage, has a name, retarding or stopping, retarding voltage or stopping potential. It stops electrons from reaching out. We can use it also to calculate Max Planck's constant, for example. Because if we know voltage, we know how much work electric field does to stop electrons, which means we know what kinetic energy those electrons had after being ejected. Yeah. If we go back to the slide, so let's say we applied the retarding potential. So now this will be a plus, this will be a minus, and electric field begins to attract electrons back. So at a certain potential, delta V critical retarding, the amount of work done on each electron will be equal to kinetic energy. So they kind of try to travel away, but the electric field brings it back. And no electron, well, again, we know that's the maximum value of kinetic energy any electron can have after being ejected. So no electron now reaches the opposite electrode. And we know that if we know this number, that will give us energy immediately in electron volts. That's it. So this is how we can measure this energy very simply by just looking at the voltmeter. Well, so again, the work function binding energy has been measured. This is a table, you can Google it, in electron volts. And if the energy of a photon is less than this number, no photoelectric effect happens. For example, a wave is composed of photons with 5 electron volts energy. If we shine it on gold, nothing going to happen. Not enough energy. But on mercury, we will see some electrons ejected. That's it. That's how it works. Well, I had this. I already had this graph. So that's the slope of this equation. Kinetic energy equals constant times frequency minus work function. Now, what else can we do? Intensity. What does intensity mean in terms of this new theory, intensity? Well, unfortunately, from historical reasons, for electric current, for intensity, people use the same letter, capital I. But intensity basically means how many photons traveling per square meter every second. So it is proportional to the number of particles. So, well, best case scenario, each photon ejects an electron, one photon, one electron. So if we increase intensity, we should increase the number of electrons, we should increase electric current, that's it. Now, where else? That was a stopping potential. Right, so when we don't apply any potential, the graph should look like this. If we apply, when we don't apply any potential and the frequency is above the critical, we should observe some current. If we apply more, we speed it up. That's not interesting. But if we flip the polarity, we start slowing down electrons, and eventually electric current becomes zero. This is the stopping potential or retarding potential, critical value. And as we know, this is the amount of work done by electric field to stop electrons, which should be equal to kinetic energy of those electrons, initial kinetic energy. And if we use two different filters, blue and green, so you can have 2 points. And if you have 2 points, again, you can calculate the slope, you can calculate the work function, anything. Basically, right here, for example, what you can do, subtract work function canceled. You know this, you know that is measured. And you can calculate the Planck's constant. That's it. And we are done with the theory. And next 6 slides, just repeat again everything what I said using written text. First slide, the description of the phenomenon. And photoelectric effect equation. And everything I said is here. And tomorrow we will solve the problem. But theoretically, any problem related to photoelectric effect can be already solved. So just do it. Go for that.